So we've been discussing models of the harmonic oscillator, but so far we've only modeled harmonic oscillators that are subject to the restoring force of the spring and a damping force. So it's a very simple model. There's two forces acting on this mass, the spring and a damping force. So today we're going to study harmonic oscillators that are subject to external forces. Like if we started shaking the table that the mass was oscillating back and forth on, or we push the mass, right, in whatever direction we want. So remember, when we derived the equation for the harmonic oscillator, we started with Newton's second law, mass times acceleration equals force. So mass times acceleration, we denote m times y double prime. If y is position, y double prime would be acceleration. And then, so that's mass times acceleration. And then on the right side, I want to put the forces, okay, because mass times acceleration equals force. And we have some assumptions about how the forces work, and that is that the force of the spring is proportional to the position of the mass. The further away from rest, the more force the spring exerts. And then the damping force, we assume, is proportional to the speed of the mass. So the faster the mass is moving, the greater the force of the damping. So we have a constant times y and a constant times y prime, proportional to position for the spring and to velocity for the mass. Okay, so this is the equation we derived. To include an external force, we have to add another term to the right-hand side of the equation, the force side. So we're going to assume this external force is a function of time only, because it's external, it's not going to depend at all on the position or the velocity of the mass. Right? So it's just going to depend on time. So some common forcing functions would be constant functions if you are applying some constant force to the mass, or an exponential growth or decay function where the force gets stronger and stronger or weaker and weaker, and sinusoidal functions where the external force oscillates, like a sound wave or shaking the table. So our new equation is going to be just the old equation plus some other external force on the right, f of t. So generally we rewrite it by, we divide everything by m so that the y double prime has a coefficient of 1. And then we say, well, b over m and k over m and f of t over m, that's kind of annoying to have to write all those fractions. So we just give them different names and we write y double prime plus py prime plus qy equals g of t. So this is sort of our simplified version of the harmonic oscillator subject to an external force. So we say it's second order, linear, constant coefficient, non-homogeneous, non-autonomous equation. So the non-homogeneous part is the important part of why this is different from other second order equations we've solved so far. Everything we've solved so far has been equal to 0, right? We've had y double prime plus py prime plus qy equals 0. That we can solve. We've done it many times. But now we're having something other than 0 on the right-hand side. That's what makes it non-homogeneous. Okay, so that's the important thing, the important characteristic of this equation. So we refer to this equation as a forced harmonic oscillator or a forced equation, and g of t is called the forcing function. So if you set it equal to 0 instead of to g of t, we call that the associated or corresponding homogeneous or unforced equation. So we solved the forced harmonic oscillator the same way we solved when we had a first order differential equation that was non-homogeneous. We do the exact same thing we did for that. So find a general solution to the associated homogeneous, find a particular solution to the non-homogeneous equation via a lucky guess in the method of undetermined coefficients, and then 3, add the step 1 and step 2 together to get the general solution. Homogeneous is when it equals 0.
I thought we said it was when you, like for
Yes. Yeah, so for first order, it was that's a non-homogeneous, and the associated homogeneous was just y prime equals a of t y, right? For second order, the non-homogeneous is y double prime equals, I move everything, well, I'm not going to move everything over, just keep it on the left. Y double prime plus py prime plus qy equals g of t. That's my non-homogeneous. The associated homogeneous is when I just take this g of t, over here it was a b of t, just take this function that's just in t and get rid of it. Y double prime plus py prime plus qy equals 0. So they're the similar, right? Right. Here I had everything on the right except for the derivative, and here everything's on the left except for the function in t. But both of them are just the non-homogeneous is when you have a term that is just a function in t, and the associated homogeneous is when you get rid of that term. So same thing you do with the first order. What we did when we were solving these guys is we would solve this one first, which wasn't too difficult, right? We could do, in this case, we could do it by separation of variables. Okay. And then we would, yeah, then we needed a particular solution to the whole thing, and then we'd add the two together and we'd have the general solution to the whole thing. So it's the same thing here. Find the general solution to the associated homogeneous, find a particular solution to the non-homogeneous, and then add those two together. That's the general solution. All right, so a couple comments before we do an example. Remember that the solutions of a harmonic oscillator with damping, right? So assuming that that damping coefficient P is non-zero, and there's no external force, right? They always tend to 0 as time goes to infinity. So if you have oscillations that are damping, they either just go directly to 0 or they kind of oscillate until they settle at 0. So the linearity principle says that the general solution to the non-homogeneous is the sum of the general solution to the homogeneous, which we know goes to 0, plus a particular solution to the non-homogeneous. Okay, so that means if this guy goes to 0, because that's the homogeneous equation with damping, then the general solution has to approach the particular solution as time goes on. That makes sense? Okay. So we call YH, that's the solution to the associated non-homogeneous equation, no external force. We call that the natural, what? Associated homogeneous, yeah. The associated homogeneous equation with no external force. We call that the natural response to the system. That's what it would do with no external forcing. And then the particular solution that we find to the non-homogeneous equation, we call that the forced response or the steady state response. So we have a little summary. All solutions of a forced damped harmonic oscillator approach the steady state solution because the natural response dies out due to the damping, leaving only the forced response. So this is just a picture of some typical graphs of a forced harmonic oscillator. So in dark blue, this dark line, that is the particular solution that we found to the non-homogeneous equation. The general solution to the non-homogeneous equation has some oscillation, but it settles down into that particular solution because the damping, the natural response dies out.
When you say the response of like hip shaking or
No, that's the forcing. The natural response is what the system would do without any external force. So like if you just set the mass to moving and the only force acting on it is the spring and the damping.
but that doesn't die out. That's
No, no, that's the particular solution to the non-homogeneous, the one that includes external force. That's the Y particular.
then you can use any
Right. The beginning is, so I get what you're saying. Yeah. Yeah. Right. Oh, right. Sorry. This thing I just labeled as Y general. This one in green is Y particular. Yeah, that's a good question. So, is there more than one Y particular? No, there can't be. If the general solution to the homogeneous equation always goes away, right? And this purple thing, well, there are different particulars for different initial conditions.
right.
Yeah. Yeah.
So this is why P almost like a, I guess there's only one particular solution.
The general, because the particular solution captures your end behavior as t goes to infinity.
Right, the whole
Yeah.
system. I didn't see that. We're
Yeah.
talking about find the solution to the homogeneous system.
Yeah. Right. And then add them together. Yeah.
This suggests there's only one solution to the non-homogeneous system. Sorry, is it a solution to the non-homogeneous system or the solution to the non-homogeneous system?
It is a particular solution because there are infinitely many more when you add on the solutions to the associated homogeneous.
For the non-homogeneous system, how many solutions do we have? One or several?
Several.
We're just using one.
So the one that we're finding is the steady state solution. It's what happens in the long run. But there are many more. They all have that same long run behavior, but different behavior when t is small. There are infinite. So here, like I've graphed several here, right? There's this purple one.
Right, but the general for the whole system, for this particular non-homogeneous solution, you're saying that there will be several that they all trend towards the same.
Yes. Okay, so let's apply our new technique. So I want to solve this general equation, 2y double prime minus 4y prime minus 6y equals 3e to the 2t. So if you remember from section 3.6, well, actually, let's write down our 3 steps. 1, solve the associated homogeneous. 2y double prime minus 4y prime minus 6y equals 0, right? So I'm just going to write down the 3 steps, then we'll come back and do them. So step 1 is to solve the associated homogeneous. Step 2 is solve minus 6y Thank you. We're trying to find a particular solution to this guy using lucky guess. Okay, and then step 3 is add 1 and 2 to get the general. All right, so we go back up here. We want to solve this, find a general solution to the second order equation. So remember from section 3.6, you can write down the characteristic equation for this without having to convert it to a system. You could convert it to a system if you want, but you can also just write down the characteristic equation. It would be 2 lambda squared minus 4 lambda minus 6 equals 0. Sure. So then this factors to minus 3 plus 1. So I get lambda equals 3 and negative 1. So I've got 2 lambdas. And I know that solutions have the form e to the lambda t, e to the 3t, and I have another solution, e to the negative t. No, not for this technique that we learned in 3.6. Because now that I have 2 particular solutions, I can find the general solution by taking a linear combination. So I would say y sub h, the general solution to the homogeneous equation, is k1 e to the 3t plus k2 e to the negative t. There was. Well, you can do it that way also. It just takes longer, yeah. This is a nice little shortcut that we learned in 3.6. All right. So finding the solution to the associated homogeneous equation is pretty quick, right? This isn't too bad. Get the characteristic equation, you get your 2 eigenvalues, your solutions are of the form e to the lambda t, and then take a linear combination of your 2. All right, so we have y sub h, good. Now we need a particular solution to this non-homogeneous differential equation. And I'm going to use lucky guess, right? Where I know that I'm taking a second derivative and a first derivative and the function itself, and I'm adding a linear combination of them up. And I'm going to try to get 3 e to the 2t. So what would you choose as a lucky guess? Alpha e to the 2t. Good. When you're adding derivatives and a function, first and second derivatives, e to the t or e to the 2t kind of makes sense because it is its own derivative. So 2y double prime, let's see, y double prime would be 4 e to the 2t. Yeah, 4 alpha e to the 2t. And I forgot the 2. Well, then my other side would be 3 halves to the 2t, so it doesn't matter. I wouldn't say it's a bad idea. 2 times 4 alpha e to the 2t minus 4 times y prime, which would just be 2 alpha e to the 2t, minus 6 times y, which is alpha e to the 2t. And that's going to, we're going to try to force it to equal by choice of alpha 3 e to the 2t. All right, so I've got 8 alpha e to the 2t minus 8 alpha e to the 2t, so those just go away. And then I have negative 6 alpha e to the 2t equals 3e to the 2t. So I set my coefficients equal. It has to be that -6 alpha equals 3, which means that alpha is -1/2. So I have found a particular solution to the to the non-homogeneous equation. Yeah, so I've got y particular of the whole thing, yep, is going to be -1/2 e to the 2t. So now I have a y general solution to the associated homogeneous. I have a particular solution to the non-homogeneous. Add them together, and I'll have the general solution to the original equation. Y general. So the original was k1 e to the 3t minus 1/2 e to the 2t. Nope. Nope. No, it wasn't. And you just added them together. Back when we did it in chapter 1, yeah. No, back when we did it in chapter 1, it was just find the general, find the particular, add them together. Yeah. We didn't have to make linear combinations until we started doing systems. Yeah, with the eigenvalues and stuff. So what do you think? Not so bad. Okay, good. Yep. All right. Why don't you try this one? I think that's supposed to be an equals, not plus. Equals 2t. So let's do it together. So step 1, we solve the associated homogeneous equation. Y double prime plus y prime minus 2y equals 0. We can do this by writing down the characteristic equation, which would be lambda squared plus lambda minus 2 equals 0. Lambda plus 2 minus 1. So -2 and 1 are my two lambdas, which means I have two particular solutions. Y1 is e to the -2t. Y2 is e to the t. To get a general solution to that homogeneous equation, I take a linear combination of these two solutions. K1 e to the -2t Okay, so there's my step 1. So that part should be easy. The hard part is the lucky guess, the educated guess. Minus 2y. Okay, so we're looking for a function that when we take its derivative, its second derivative, and itself, add them up, we get something linear. As a general rule, your lucky guess usually works if you take a function of the same form as your forcing function. So I'm going to take a linear function. So my lucky guess would be alpha t plus beta. So when the forcing function is exponential, we take an exponential. Linear, you take a linear. There are some problems where it's well, with trig, you're going to also take trig. Yep. There are some problems sometimes when it doesn't work, and we've seen them in the chapter 1 style, and in those cases, you can do that, or you can guess again, and your second guess adds. We just add something sometimes. I don't know. Good question. All right, so let's see. Y double prime would be 0. Y prime would be alpha minus 2 times y. Distribute that -2, alpha minus 2 alpha t minus 2 beta equals 2t. Then on the left side here, I'm going to collect my t's. Now you set corresponding coefficients equal, right? So my coefficient of t on the left is -2 alpha, and on the right it's 2. So those have to be equal. -2 alpha has to equal 2. And on the left, I have a constant term of alpha minus 2 beta, and on the right, I have no constant term. So alpha minus 2 beta has to be 0. Okay, so that means alpha has to be -1, and beta has to be -0.5. So my y particular is going to be alpha t, -t, plus beta minus 0.5. Okay, so my general solution to the original non-homogeneous equation is y sub h plus y sub p. So -2t and t. And then I think you factored wrong. I think it's -2 and 1 minus. So is this your characteristic equation? Lambda squared plus lambda minus 2 equals 0. So you get +2 minus 1, -2 and 1 are the solutions. All right, so now I have 2 initial conditions and 2 unknown parameters. So I use my initial conditions to figure them out. So I know that y of 0 would be k1 plus k2 minus 0.5, and that's supposed to equal 0. And then y prime of 0, so I'm going to take y prime and plug in 0 at the same time here. So I get -2 k1 plus k2 and minus 1 equals 1. So 2 equations, 2 unknowns, not so bad. So here k1 is 1/2 minus k2. Plug that in here. -2 times 1/2 minus k2 plus k2 equals 2. I moved the 1 over. So I have -1 plus 3k2 equals 2, which means 3k2 equals 3, so k2 is 1, and k1 would have to be 0.5 minus 1 is -0.5. So now I have k1 and k2. Those aren't the answers. Those are just the coefficients you plug into the equation. So it's just a common thing that I see sometimes, like you just circle the k's and move on, right? But that's not the answer. The answer is you're one step short of the answer. Y equals. And then K1 is 1, so we've got plus e to the t. Do you have a question? Did you just ask me something? Uh-huh. So I got to solve this system, and what was lambda? 2. Okay, so lambda equals 2 repeated is my eigenvalue. Okay, so then the general solution. So yeah, so we. Okay, so that one was just special. And then we come up with the, hang on 1 second. Here it is. That's how you find the, that's the general form for the repeated 3, 5. So it's e to the lambda t v naught, and v naught is the initial condition of y of t, and v1, and then you have times plus t e to the lambda t v1, and v1 is either an eigenvector or the 0 vector. Okay. Yes. One second, I'm just going to copy this. Correct. Yeah.
So it's like kind of not a okay, well, so it's sort of like so we could just say we could say K1.
Yeah, you could. It's just that they happen to be the initial conditions, so we should, like, why not just say that that's what they are? Yeah. Okay, so my general solution is going to be y equals e to the lambda t v naught plus t e to the lambda t v1. Okay, so I now know lambda is 2, so put that in for the 2 lambdas. V naught and V1, one of them's an eigenvalue, one of them's the initial condition. So V0 is the initial condition, right? So I just plug in 0, 0 into my system, 0 for Y, 0 for V, and I get 0, 0, my initial condition, right? Oh yeah, we don't know that. We don't know that. Okay, sorry. Yeah, it's just X naught, Y naught. Y naught, V naught. And V1 is the eigenvector associated with lambda, right? So we solve that by doing AV equals lambda V. How we always get it, right? Okay, so my A was 0, 1, negative 4, 4. No, that's how you find the eigenvalue. We already have the eigenvalue, but because we.
I have it shown as V1 equals A minus I.
Right, that's a shortcut, but we don't happen to know V0, so.
Okay, just say
It's not.
Yeah, we could do that. Okay, so say it again. V1 is what?
A minus I.
3.5. So yeah, A is 0, 1, negative 4, 4, minus. Okay, so I'm going to get my new, this is going to be negative 2. 1 minus 0 is 1. Negative 4 minus 0 is negative 4. And 4 minus 2 is 2. And multiply that times y naught v naught. No, multiply them out. So you'd have, because now then it'll just be a vector, negative 2 y naught plus v naught, and negative 4 y naught plus 2 v naught.
So that's your I. So you do your initial.
Yeah.
I did the
V naught equals y naught v naught.
Yeah, where did that happen?
Oh, that's just a vector notation thing. So like, so y naught is your initial condition, and it's bold, and it's representing the vector yv.
Oh.
Right. Yeah.
Now I feel like we should get it. We just did A, B.
Yeah. Yeah. Yes. Well, so here's the thing. This is a vector, right, that depends on the initial conditions. Yeah, that will definitely give us a vector with just numbers. This is an infinite number of vectors, right? It depends. So we could find a vector that makes this true, or I could go up here and do this.
I don't get why this works.
I know. Let's see what happens when I do this. I get v equals 2y and negative 4y plus 4v equals 2v.
That was just the Y harmonics, right?
Yes. That's one part of this problem. Yeah.
But these guys' smart idea was
Because I'm just going to take a step back. How do you solve this? What have we been doing? Because if I have to do it on my own, that's not happening. I don't know what.
No, so what happens is we always get an infinite number of, when we find an eigenvector associated with an eigenvalue, it always comes out infinite. They're straight line solutions, right? So like here, there are an infinite number of y's and v's that will make these two equations true, and we usually just pick one. Yeah. So I could do the same thing here. Just pick one. Yeah. Any y naught v naught that will. But that's not an equation, so I don't know. I gotta think about it. Yeah. Yeah, so like for this would be, so 1, 2 is the I don't know why this isn't working. I'm gonna think about this and tell you on Monday. I don't know. I gotta think about it.
This is the thing that's.
Well, why can't? Because I could just use 1, 2, and that's so much prettier as my eigenvector instead of that.
How is that? So you want?
That's the eigenvector associated with lambda equals 2. What was it?
That was the only way we did it. Yeah. That was what we had to do.
No, we had to do it the first way.
No, in class. Yes. If you didn't have a do something, you had to do it.
Let's all reread 3.5
Yeah.
and discuss it on Monday.